So in this problem, we have this particle that's moving down a ball, and then we want to find the condition where such that the ball never moves. So the first thing to realize is that the ball is moving. The ball will move because there is a normal force acting on the particle. So you can imagine the particle is going down right now, and then this is a snapshot of it going down, and then right at this very moment there is a normal force acting on the particle. So it's causing it to go in a sort of circular motion. And then this normal force that's exerted on the particle is always also going to be exerted on the ball as well. So you can imagine a normal force going in the opposite direction that's acting on the ball, and that is going to cause it to move. And the only thing that's going to stop it is friction. So in order to find the conditions that we need, I think it's pretty obvious that we actually need to find an expression for normal force first. So by finding the expression of normal force, we can then set up some conditions that will help us find the expressions, this ratio that we need. So what exactly is normal force? So in order to find that, first we can consider the centripetal force that's acting on the particle. Well, centripetal force is equal to mv squared divided by the radius of the ball. Let's call it r for now. So this is the centripetal force, right? So this is going to be equal to two things. It's going to be contributed by two things. So first of all, of course, there's a normal force, but then there's also gravity. And you can actually break up gravity like this. So you see that for gravity, there's also a component that's pointing along in this radial direction. And so the centripetal force is going to be the net force between this normal force and this gravity. So first of all, let's define centripetal force. We're going to need to know what mv squared is. And we can do that by considering energy, because we're told that the ball is frictionless. So for energy, we can set up the equation kinetic energy is equal to the amount of potential energy loss. And that's just mg times the height, the decrease in height. Now let's call this distance r. So that's just r sine theta, which is this distance over here. So you can imagine this part being the top of the ball. It's going down. So you see that mv squared is equal to 2mg r sine theta. So we can substitute this directly back into here for a centripetal force. That gives us 2mg r sine theta divided by r equal to 2mg sine theta. So this is centripetal force. So it's going to be a net force pointing to the center of the ball. Now this is going to be equal to the normal force, which is also pointing in this direction, minus this gravity component that's pointing in the opposite direction. Well, this component here, again, we can calculate that using trigonometry, and we're going to have to do a bit of geometry here. So this is 90 degrees, this is theta, so this is 90 minus theta. And these are just like opposite angles, so this is also 90 minus theta. And because this is 90 degrees, then this angle must be theta. So if this is mg, then this component here is mg sine theta. So we find that n is equal to 3 mg sine theta. So we've done the first step. This is our important result, the normal force. And second of all, we can find the amount of force that is acting along in a horizontal direction of the ball. So this is a normal force that is causing the centripetal force, the circular motion of the particle, right? And this normal force is going to have a horizontal component. So if this arrow here is the normal force that is acting on the ball, there's going to be a horizontal and vertical component. This vertical component is going to push the ball onto the ground harder, and then the ground is just going, the surface of whatever the ball is lying on is just going to counteract with a stronger normal force. This horizontal component is going to be counteracted by friction. So in our case, as we know, we're interested in friction, so that's why we actually need to find this horizontal component. So again, we can do trigonometry and a bit of geometry. We just found out that this is 90 minus theta, and if this is 90 degrees, then this is also theta. So now using, if this arrow here is the normal force acting on the ball, then this horizontal component, so let's just say this is the horizontal component acting on the ball due to the normal force, that's just equal to the normal force times cosine theta. So this is another important result. This is the force that is pushing on the ball that is causing it to move. So you can imagine the particle being here, there's a normal force, and this normal force is going to be pushing onto the ball as well, and there's going to be a horizontal component that is going to push, make the ball move. So we're going to have to consider this force if we want to find the conditions where it won't move. So this is an important result as well. So the first thing you might think, we're actually almost essentially done. So we can just find when this function is going to be maximized, and then we can just say when this sine theta cosine theta is maximized, let that be equal to friction. So, and if the maximum horizontal force is already counteracted by friction, then we're essentially done. And you'll find that the maximum of this function actually happens when theta is equal to pi over 4. But then there's actually a catch, because as this particle travels down, it's also going to exert greater downward pressure onto the ball. So that's going to increase the normal force that is acting due to the ground. And that is going to increase the potential amount of friction that is going to be exerted by the surface. So we have to take that into account as well. So we need to take account of friction. So the expression for friction is normal force times the friction coefficient. So in our case, we're given that the coefficient is equal to 1. So right here, I'm just going to solve for the general case. I'm just going to assume it's some constant mu. So in the end, we're just going to substitute 1, but I'll just solve for the general case now. Well, the normal force that is acting on the ball at this surface over here is equal to mg. This m is due to the ball itself, and then another component is due to the vertical force caused by this normal force that is caused by this particle that's sliding down. So just now we found the horizontal component of this force, and then to find the vertical component we just do something similar, and in our case we just switch the cosine for a sine. So that's just going to be equal to 3mg sine squared theta. So instead of equal, actually I should put inequality sign. So this is the largest possible friction. So friction is only equal to however much friction you need to counteract whatever force that's trying to push this thing. So if there's only a slight amount of force, there's going to be a slight amount of friction. So friction is always only going to reach this level when the force that's acting on the ball actually reaches or exceeds this level. So this is the maximum possible friction. And using this, we can try to find the ratio that we're looking for.